Hey everyone, my name is Danny Senor, and I'm going to be teaching you guys or informing you guys about Newton's method by understanding the history and understanding when to apply his method in calculus, obviously. So, one of the first things is that I want to inform you guys about is Newton's history or the Newton's method history, as in the background and things like that. So, Isaac Newton, well, to start with, Isaac Newton was one of the main contributors for calculus. And the reason because of this is because although Sir Isaac Newton was mainly known for his laws of motion and his focus on gravity, things like that. One other things other than that is that one of his other most biggest breakthroughs and biggest things that he's famous for is actually for his discoveries and for his work in mathematics, more specifically calculus, to be exact. Newton's method was actually published at around 1685, give or take. There's a lot of information going out saying that he posted in a later date or he was published in an earlier date, things like that. But more often than not, I'm finding that it's around 1685. Sir Isaac Newton was the actual discoverer of calculus, him and many other people, of course. Um, and quite often than not, most people even call him the father of calculus. Now, the next thing I want to talk about is Newton's method, definition, and its significance. Now, let's start with Newton's method, obviously. Newton's method is could be known as recursive algorithm for approximating the root of a differential function. Newton's method for solving equation is another numerical method just for finding things such as f of x is equal to 0. It is even based on the geometry of a curve using tangent lines to a curve. Hence, it needs calculus, but if you want to be more specific, it needs differentiations. Differentiations, sorry. Now let's start with the algorithm for Newton's method. To begin with, the first thing that we see, sorry, uh, the first thing that we see on the very top is x2 is equal to x1 minus f of x1 over f prime of f of x1. What is this? Well, this is one of the very first things that we're supposed to look at when doing Newton's method. Overall, that is the main formula that we're always going to be using when doing Newton's method, give or take, right? Um, Now, if we're going to do this correctly, we're going to go starting from x2, we perform the same calculation and obtain the approximation x3. And when we do that, we see the second formula in the bottom, or in the middle, sorry, which is going to be x3 is equal to x2 minus f of x2 over f prime of x2. Okay, then what do we do then? The same calculation applies to each stage. So if we're thinking about this logically, for the nth approximation, xn, the next approximation is given by xn plus 1 is equal to xn minus f of xn over f prime xn. It's kind of a handful, really, to think about. So the way I thought about this is I tried giving it the most easiest way to think about. If we're looking at it correctly, Newton's method, let's do let f r going to r is being differentiable function is to be a differentiable function, sorry. We seek a solution of f of x is equal to 0, starting from an initial estimate x is equal to x1. At the end step, given xn, compute the next approximation, which is going to be xn plus 1 by using the formula as we see below, which is going to be xn plus 1 is equal to xn, subtracting f of xn over f prime of xn of xn, sorry. And then we repeat the process over and over again until we find what we need to. So how do we do this? How do we apply it into an equation, for example? Well, for this example, we're going to look at the formula or the equation x squared minus 2 is going to be equal to 0. So what do we do? Well, the equation is that we're looking at is going to be to use Newton's method to find an approximate solution of the equation, and we're going to start from the initial estimate x1 is equal to 2. Now, after 4 iterations, how close is the approximation to the square root of 2? So the first things that we're going to do is that we're going to let f of x is equal to x squared minus 2. So f prime of x is equal to 2x. And now at step 1, we're going to have x1 equal to 2. And then we calculate f over x1, or f of x1, sorry, is equal to 2 squared minus 2, which is obviously going to be equal to 2, correct? Then we're going to do, and this is also going to mean f prime of x1 is going to equal to 4. So what does this leave us? Well, we're going to look at the equation, or the walkthrough that is going to be at the very top. It's going to be x2 is equal to x1. And then it's going to be subtracting f of x1, which is over f prime of x1, which is going to be equal to 2, minus 2/4, which is going to be equal to 3 over 2, which is all throughout going to be 1.5. We're not finished there. So we're doing a step 2, which is going to be somewhat the same thing, which we're going to do x2 is equal to 3 over 2, which we calculate f of x2 is equal to 1/4, and f prime of x2 is going to equal to 3. So we apply somewhat of the same process, but obviously with different numbers, and we're going to leave somewhat to about 1.1 or 1.416666, give or take. Then at step 3, we're going to do the same thing, but we're going to do from x4 is equal to 577 over 408. Then we calculate f of x4 is going to be equal to 1 over 166,000 to 464, sorry. And that's going to be f prime of x4, which is going to be equal to 577 over 204. So what does this leave us? If we think about this logically, and if we try doing the calculations, the same as we always did, it's going to leave us to 665,857 over 470 and 832,000, which roughly, give or take, if we put this in the calculator, it's going to be 1.41 1.414213562375. And in fact, if we put 12 decimal places for the square root of 2, which is going to be roughly about 1.41, after 4 iterations, the approximate solution of x5 agrees with the square root of 2. That applies to 11 decimal places. The difference between x5 and square root of 2 is that it's going to be somewhat around 665,857 over 470, 832, subtracting the square root of 2, which is going to obviously give us 1.59, multiplying 10 over the negative 12 power, which is going to be 3 significant figures, sorry. Now we're going to do it for another problem. So, if you're thinking about this, if we find so right here in this one, we are going to have to approximate pi by using Newton's method to solve sine of x is equal to 0 for 3 iterations from x equals 3, sorry. So, thinking this, we're going to have to find out how many decimal places is it going to take to find the approximate solution accurate. Now, we're going to do our very first steps. We're going to let f of x is equal to sine. So f prime of x is going to equal cosine of x. We compute this x2, x3, x4 directly using this formula. xn plus 1 is equal to xn, subtracting f of xn over f prime of xn. And that's going to equal xn minus sine xn over cosine xn, which that in terms is going to equal to xn minus tangent xn. It's kind of a little confusing me talking about it, but it makes a little bit of sense if we're just thinking about this algebraically. Um, then we compute directly each xn to that 25 decimal places for 3 iterations. Um, and then we're going to do x2 is equal to x1 minus tangent x1 is equal to 3 minus tangent of 3, which is going to be approximately 3.142546554, and etc. And we're going to do that again. It's going to be x3 is equal to x2 minus tangent of x2. So it's going to be 3.145926533040047615449, and so forth. Let me do it again. X4 is equal to x3 minus tangent x3, which is going to be roughly about 3.14159265358979238462644. Now, if you look at the three, you can see a difference that all three of them, at the very end, they're all going to have different numbers, which in a sense makes kind of sense, right? So up to 25 decimal places, the pi is going to be 3.4159, and etc. It's going to be agrees to 24 places. Now, when can it go wrong? When can Newton's method misfire? For this example, while Newton's method can fantastically give good approximations to the solution, several things can go wrong. Now we can examine for this less fortunate behavior. For this example, we're going to look at find a solution of sine x is equal to 0 using Newton's method starting from x is equal to pi over 2. Now, if we see this logically, we could see how f of x is equal to sine x, so f prime is going to be cosine of x. And if we use this, it's going to be equal to 0, which we cannot do. In using Newton's method, we cannot equal anything to 0. Or divide by 0, sorry. Now, if we do this again for another one, we're going to look at somewhat the same problem. Approximate solution, negative x3 plus 4x2 is equal to 2x plus 2 is equal to 0. Now, for this equation, we're going to look at the computation for x4 is the exact same as for x2. So x4 is equal to x2 is equal to 1. Thus, xn is equal to 0, which, again, is a misfire. So if we're going to think about this logically, if xn is equal to 0, then Newton's method immediately fails, as it attempts to divide by 0, which is never good. The approximations x1, x2, x3 can cycle rather than converging in solution. The approximate solution x1, x2, x3 can even diverge to infinity. This problem happens when f prime of xn is small but not 0. If we apply Newton's real method to the real world, we can notice that it does in aeronautical engineering, astronautical engineering, mechanical engineering, solving scientific problems, and so forth. And this is my bibliography right here. And thank you, and I hope you learned something. Thank you so much.